Hello, my name is Ross Adams. I want to give a presentation about the Silver Bridge disaster. Introduction. On December the 15th, 1967, at about 5 p.m, the bridge carrying US Route 35 connecting Point Pleasant, West Virginia to Gallipolis in the state of Ohio toppled into the Ohio River. 31 vehicles fell with the bridge, resulting in the death of 46 people, 2 of whom were never found. An inspection of the bridge had been done 2 years prior to the collapse, and some $30,000 in recommended repairs were completed. 3 more inspections had been carried out in 1967, in the years before its demise. In the years before its demise, people had reported experiencing an up and down motion when crossing it. An overview of the findings. In the days after the collapse, the National Transportation Safety Board immediately began an investigation into the failure of the bridge. The investigators reconstructed the bridge from pieces laid out in a field. The bridge was called the Silver Bridge because of the colour of its aluminium paint. It had effectively been a suspension bridge, but one that used eye-bars and rigid hangers to support the deck, rather than the familiar steel cables of modern suspension bridges. In this arrangement, each chain link consisted of a pair of bone-shaped 50 by 305mm bars, varying in length from 14 to 17 metres, with their position on the bridge. Pins of 280mm in diameter connected the links through the eyes at the ends of the bars, as this picture shows. After extensive laboratory studies of the broken structure members, the cause of the failure was determined. It was attributed to a cleavage fracture in the lower limb of the eye bar 330 at joint C13N of the lower eye bar suspension chain in the Ohio side span. The old saying, "a chain is only as strong as its weakest link," turned out to be a fact in the failure of the Silver Bridge. The board also found that when the eye bar broke, the resulting asymmetric load on the pin caused it to twist, and the single eye bar that was left vibrated off the other side of the pin, at which point the chain was completely severed. The adjacent tower, being destabilised, started toppling to the north. The road below twisted over, and the other tower was pulled down into the river as well. A closer look at the nature of the engineering failure. At the time of the construction of the Silver Bridge in 1927, eye-bar bridges had been built for about 100 years. Such bridges had been usually constructed with redundant bar links, using rows of 4 to 6 bars, sometimes using several such chains in parallel. An example can be seen in the Clifton Suspension Bridge designed by Isambard Brunel. The chain eye bars are redundant in 2 dimensions. The company that built the Silver Bridge also built an eye bar suspension bridge still in use today in Pittsburgh. The steel used in that bridge is of lower strength than that used in the Silver Bridge, but it has been said to have a safety factor of at least 2. That means it is designed to support more than twice the greatest expected load. Its multiple eye bar link assemblies provide multiple load paths. After constructing the bridge in Pittsburgh with multiple eye bars, the American Bridge Company went on to construct the Silver Bridge in 1927, and its sister bridge, the High Carpenter Bridge, 75 miles upstream the following year. These bridges were engineered by a different designer who embraced a new high-carbon, high-strength, heat-treated steel. Presumably he thought that meant that a less substantial structure could be built, and as such the eye bar links in these 2 bridges were not redundant, as links were composed of only 2 bars each, albeit made of high-strength steel. They were more than twice the tensile strength of common mild steel. With only 2 bars, the failure of one could impose excessive loading on the second, causing total failure, which would be unlikely if more bars were used. While a low redundancy chain can be engineered to the design requirements, safety is completely dependent upon correct high-quality manufacturing, assembly, and maintenance. Undoubtedly, the designer of the Silver and High Carpenter bridges expected a lower loading than in Pittsburgh. Also, each bridge was a much longer span, and so the loads at the tops of the chains in the towers would have been greater than in the Pittsburgh Bridge. The towers themselves were less substantial structures as well, yet the designer felt sufficiently confident in the new material to proceed. The 2 new designs had a safety factor of 1.5 when they were built. In 1927, at the time of the Silver Bridge construction, a typical family car was the Ford Model T, which had a weight of about 680 kilograms. The maximum permitted gross weight for a truck was about 9 tonnes. By contrast, at the time of the collapse in 1967, a typical family car weighed about 1,800 kilograms, and the large truck limit was 27 tonnes or more with a special permit. Also, traffic jams on the bridge were much more common, occurring twice or more a day, 5 days a week, thus causing more stress to the bridge elements. Indeed, the disaster happened at rush hour. Civil engineers could not see that 40 years after the bridge's construction, their traffic loads would more than triple. In the Silver Bridge, the links were made from high-strength steel that had been developed in the 1920s by the American Bridge Company. This new steel would allow the individual members of the bridge to handle more stress. With the 2 I-bars sharing the load, it was thought that the steel could easily handle the 1,820,000 kilogram load. The I-bars had been cast to shape and then heat treated to develop the strength of the steel. Then the holes were drilled out. Following the failure, the collapsed bridge needed to be thoroughly inspected before the cause could be determined. When the fractured I-bar link number 330 was found, investigators from the National Transportation Safety Board could determine what happened. A small crack was formed through fretting wear at the bearing of the hole drilled in the I-bar. Fretting refers to wear and sometimes corrosion damage at the asperities of contact surfaces. Asperity is the unevenness of a surface. This fretting is induced under load and in the presence of repeated relative motion. People who use the bridge noticed an up and down motion. It degrades the surface layer quality, producing increased surface roughness and micro pits, which reduces the fatigue strength of the components. The small crack formed through fretting wear grew through internal corrosion, a problem known as stress corrosion cracking. The design of the I-bar assembly meant that water could pool at the bottom of the eye hole, and the combination of tensile residual stress created through its heat treatment at manufacture and the corrosive industrial environment had caused a stress corrosion crack to form. Hidden away, the crack had grown slowly over 39 years until it was about 3 millimeters long. Also, the steel used in the I-bars had a low toughness at the near freezing temperatures on the night of the disaster, making it susceptible to brittle fracture. The critical brittle crack, which brought the bridge down, occurred at right angles to the I-bar shank, where the bearing surface would connect with the pin. When the last side of the I-bar failed, all of the load was transferred to the other side of the I-bar, which then failed in ductile overload. The joint was then held together by only 3 I-bars, and another slipped off the pin at the centre of the bearing, so the chain was completely severed. A collapse of the entire structure was inevitable, since all parts on a suspension bridge are in equilibrium with one another. Afterwards, witnesses estimated that it took only about a minute for the whole bridge to fail. The damage to the link would have been difficult to see during inspection of the bridge, and inspection prior to construction would not have been able to notice a tiny crack. The technology used for inspection at the time was not capable of detecting such cracks. Perhaps ominously, an article in the Engineering News Record from 1928, when the bridge was opened, noted the fact that it was not possible to make any adjustments in the chains, hangers, or trusses after erection. Recommendations for what the engineers involved could have done differently. In the first place, it would be recommended that at least 4, if not 6, eye-bars be used in every link in the eye-bar suspension chain. Also recommended would be that the heat treatment used in giving the steel high tensile strength at manufacture not be undertaken, thus avoiding imparting residual stress to the eye-bars. It is also important that a steel with toughness at freezing temperatures be used. It is suggested that a suspension bridge span not be too long. More rigorous construction techniques need to be employed where the span is very long, and wind loading needs to be compensated for with such methods. The engineers of the day didn't have a comprehension of the errors in design that would be foisted upon unfortunate users of the Silver Bridge nearly 4 decades into the future. Conclusions. The Silver Bridge was a more price-competitive design than one using steel cables for suspension, as had begun to be used in bridge construction around the time of its commissioning. The lesson here is that there are situations where expense shouldn't be spared, as when the safety of the public is at stake. The bridge's towers were also unsubstantially built, preventing them from effecting remedial action in the event of the disaster. Noted in the report issued by the Safety Board were findings that in 1927, stress corrosion and corrosion fatigue were not known to occur in the bridge materials used under conditions of exposure normally encountered in rural areas, and that the location of the minute crack was inaccessible to visual inspection and could not have been detected by any method without disassembly of the eye-bar joint, which was a practical impossibility. It is advantageous, therefore, that suspension bridges using eye-bars in their construction went out of fashion after this disaster. The engineering historian Henry Petrosky writes that the cause of the disaster was found to be a design that inadvertently made inspection all but impossible and failure all but inevitable. If ever a design was to blame for a failure, this was it. If there is anything positive about the Silver Bridge failure, it is that its legacy should remind engineers to proceed always with the utmost caution, ever mindful of the possible existence of unknown unknowns and the potential consequences of even the smallest design decisions. And the following are a list of references that I used in making this presentation. Thank you for watching and listening to my video.